Welcome back, everybody. This is AP Chemistry, Unit 11, Section 2, taking a look at Hess's Law. And what Hess's Law is talking about is overall, to get a reaction to go, either you need to invest energy, that's endothermic, or you'll actually expend energy or emit energy as an exothermic. And sometimes reactions take more than one step to get to its final state. And so let's take a look at a simple example of this with the combustion of carbon into a combustion of carbon into graphite, and then that graphite will then also form my diamond. Okay, and so typically with this, when we see examples like this, we'll be given how much energy it takes to do a single step, and then we'll apply Hess's law to this. So we can see that graphite, when they say combustion, graphite ends up being combusted, and so what we get is oxygen, and that'll give carbon dioxide, and typically there's going to be water if it's a combustion, but in this case it's just pure carbon, so there's no hydrogen there. And they tell us that the energy emitted from that is 394 kilojoules. Okay, but then they also give this other information about the combustion of diamond. And so if I get diamond and I combust that, I'll get carbon dioxide, and that combustion will give off negative 396 kilojoules. Well, it won't give off negative, but it has a delta H of negative. But you see, the problem is we're going to take graphite and create diamond. Here, diamond is my reactant. So I need to flip the entire equation to get this entire process in place. So in other words, I'm going to be decomposing my carbon dioxide to get my diamond, and I'll also get oxygen off of that. And when I flip the reaction, I also flip the sign. I will invest 396 kilojoules of energy. So what we just did is we said this first step as a reactant, to get that, I emitted 394 kilojoules. But then to decompose my carbon dioxide, I will have to invest in 396 kilojoules of energy. And so Hess's law says you just simply add those up. And you can see that we end up with a delta H of being 2 or plus 2 kilojoules per mole. What that tells us is that this process is endothermic. Okay, it does require energy to get graphite into that diamond. Okay, not as much as a person might think, but it does require energy. So that's the simplest example of Hess's law in place. And so let's take a look at a couple other examples of this. One would be for the formation of diborane. Now there's actually 4 different steps that have to take place to get my diborane. And notice that this is ultimately the net equation overall. What has to happen is I get this equation. So you see, this first step looks pretty much okay. We got 2 borons and 2 borons. Okay, now it's going to be producing this the B2O3 in there. Okay, so I can rewrite that step because it is pretty much right in line with what we need. And this is going to be of a gas, and it's going to be forming the B2O3. That's a solid. Now do keep track of your delta H's and be very, very clear on your negatives and positives so you don't screw yourself up. This is a negative 273. Now the next step in this, we see that we find my diborane. Okay, but notice that it's on the reactant side, and it needs to be in the product side. There is one of them here and one of them here, but we do need to flip the equation, don't we? And so in step B, I'm going to take this B2O6, that's a solid, and I'm going to get my 3 oxygens, that's a gas, and that will use up the B2O3, that's a solid, and 3 waters. Okay, so that process, I had to flip the equation, and so I'm going to be flipping the sign. That's a plus 2035 kilojoules. Okay, so you'll notice that we've accounted for my B2O3 already. Okay, now we've got some oxygens, and notice that these aren't matched up yet, but we're not done yet with the whole process. Let's take a look at letter C. The letter C says we've got this liquid water in here, and we're going to be investing in some of the oxygens. Okay, so this oxygen, when we look at this step, we need to actually triple that oxygen, and that's because we need to account for, or sorry, triple the equation, because notice here I've got 3 hydrogens and I only have 1 here. So let's triple everything in this line. And so we can keep it in the same set that it is, but I'll need 3 hydrogens and that's in its solid state apparently, and 3/2 of my oxygen, there's my gas, and that will triple my water, that's a liquid. And when I triple the equation, I also triple my energy. So my energy, my delta H, ends up being 3 times the negative 286. I didn't actually flip the equation, so the sign stays the same. Now we see that I've accounted for my hydrogen is in there, my boron is in there. That's looking good. And so now we have to account for my oxygens. Here I've got 3/2 and 3/2, and here I've got 3. Well, we have one more step in this whole process, don't we? Okay, so 3/2 and 3/2, that's 6/2, and 6/2 is 3. So these two will cancel out with this one. So now what do we have left? This water was a liquid in this step. And this water was a liquid in this step. And so notice, let's see, up here in B, this was actually water as a gas. I'm sorry, there's the water gas. This is water that's a liquid. So I need to account for that. Notice that liquid water is on this side, so it's H2O, and that's a liquid. That will cancel. And here's my water. That will cancel on this side. But you see the problem. The liquid water, there's 3 here, and there's only 1 here. So I'm going to have to triple this, and that means I have to triple this, which is probably a good thing because this guy is triple as well. So you see that my hydrogen, or sorry, my delta H is 3 of these, and that's plus 44 as well. Okay, so if I do all that, I add it all up, notice that my waters are gone. Those are all accounted for, and I do in fact have this equation. Now I can add everything, and my delta H ends up being plus 36 kilojoules. That is endothermic again. And when you're trying to make rocket fuel, and use it, probably not a good idea, because it's going to constantly require that energy in there, and it's a waste of energy to do that process. Okay, there's simpler ways to do it. That's why you use hydrogen and oxygen now. Okay, now let's take a look at another one. And with this equation, we're going to be seeing that we're going to take nitrogen and oxygen, and we're going to make N2O5. Okay, given that information, we have to kind of bounce between these, don't we? If I have to do this, notice that I end up seeing my N2O5 is a reactant here. I need to flip this equation. Okay, I need to actually get this so it's N2O5. That's a gas, and my water, that's a liquid, and I need to get that as a product, and I have my HNO3, that's a liquid. Now the reason I kind of left off the number here, the coefficient, notice that I need 2 of these, and I only have 1, so I'm going to have to double everything. Okay, since I started already with my, let's see, where'd I go? With my 2 here, that means I must have 4 here. That delta H ends up getting doubled. And I did flip the equation too, so that's a plus 76.6. Okay, so that ends up, if I do that, that ends up being plus 153.2 kilojoules. Okay, now if I see this, then I also, let's look down at some other things. Here I've got my nitrogen and my nitrogen. Well, I need to, it's in the right spot and everything, but I see, I've got an issue where I've got 2 of these and a half of those. I've got oxygens that I see here and here. So they're in the right spots, but I'm going to have to kind of see what happens with all this as I go. Let's take a look and let's evaluate this line right here. Okay, my ending nitrogen, or sorry, to get my nitrate here, I need 4 of these. Okay, that means that I have to multiply this by 4 as well. Okay, so I don't have to flip this guy, but I do have to multiply everything by 4 so that I have 4 nitric acids here. Okay, so let's make my 4 nitric acids. NO3, that's a liquid. And so that makes this a 4. 4 times 1 is 4 divided by 2. That will give me 2 hydrogens. That's a gas. 4 times 3 is 12, divided by 2 is 6 oxygens. And 4 times 1 is 4, divided by 2. That gives me 2 nitrogens. Okay, which is actually really nice because that's what I needed in the first place. So if I did that, I had to multiply everything by 4. I did not flip the equation, so it is still a negative 174.1. And so that ends up being negative 696.4 kilojoules. Okay, so notice that my nitrogen is locked. My oxygen I'm going to have to get rid of, at least some of them. I have 6 and I need only 5. And you'll notice I've got my nitrate is taken care of. That guy is gone. All right. So now I see that I have also my water. And you see that this guy, the water, is a product. Let's flip the equation. Okay. I'm going to get rid of that water there. There's my water. And I saw that I had H2. That's a gas. And my 1/2 oxygen. That's a gas. But on this side, I have 2 waters. Let's double everything. That's 2 waters, 2 hydrogens. 2 times 1 is 2. Divided by 2 would be 1 now, oxygen. And I'm actually going to write the 1 in there. Okay? So that takes care of this. And remember that I doubled everything and I flipped it. So my delta H is going to be a plus 258.8. But I doubled everything. Okay? So that ends up being a plus 517.6 kilojoules. Okay, now here's what we did. Here, my water is gone, and so I've got my 2 hydrogens. Uh, let's see, and that's 2 hydrogens here. And so I've got 1 oxygen, and I've got 6 oxygen. So one of these is going to eat up one of these. Okay, that oxygen's gone, but I'm left with 5 oxygens, and that's what my equation was asking for in the first place. Okay, so everything's accounted for here. I have 2 nitrogens, I have 5 oxygens, and I have 2 of the N2O5s, and so everything is good. I simply add all this up, and I end up with a delta H. If I did all my math right, is negative 25.6 kilojoules. This problem is exothermic, and the problem is solved. Okay, now let's take a look at one more set of things, and so we can kind of finish up this unit just to see what we've been doing. Now, a little bit of text here. The standard enthalpies of formation. So basically, those values that I've been giving you all along is equal to the enthalpy change when 1 mole of the compound is formed at a constant pressure and at a fixed temperature. Okay, most of those enthalpies of formation are negative numbers. Most of the time, they're exothermic. Okay, but do keep in mind that elements, when they're in their standard states, have a standard enthalpy formation equal to 0. It doesn't take any energy. That's what state they prefer. So some things to keep in mind. If a reaction is reversed, the magnitude of all the heat remains the same, but the sign changes. Okay, we just changed the sign with that. When the balanced equation for that is multiplied by an integer, we did in fact have to multiply that H value as well. And also keep in mind that if you have just a single element in its natural state, that standard state is 0. So let's see what we can do with that if we want to find my delta H given information like this. Okay, I'll need to consult my charts for this. And by that, I mean the heat of formation for some different compounds. Notice we're trying to find my delta H, and it's the summation of the heats of all of the products minus the heats of all the reactants. Okay, that's the formation of those. So from this, I just kind of take a look and I see, okay, we have delta H, and so of my ammonia, that, if I look up, is a negative 46.11 kilojoules. Okay, there's my ammonia. If I look up my oxygen, well, remember, it's in its natural state. So the heat of formation for oxygen is going to be 0 because it's in its natural state. Now I take a look and let's find my heat of formation for my nitrogen dioxide. Okay, that ends up being a 33.18 kilojoules. And let's look at the heat of formation. Now remember, water is a liquid in its state, but it's not an element in its natural state. So I do have a heat of formation for water as a liquid, because it's going to be a little bit different if it's a gas. It's a negative 285.83 kilojoules. Okay, so now let's apply my formula for figuring out the total of all of this. Okay, so my heat of formation for the entire equation is going to be the summation of everything that we've got here. Well, I have my products. I have 4 times my nitrogen dioxide. That was 33.18 plus my water. That's 6. There we go. 6 times the 285.83. Okay, so that plus the summation of my reactants. And remember, my oxygen didn't do anything. So I simply have 4 times my negative 46.11. Okay, so if I do all of that math, I end up with, and I guess I could just go 7 times 0, for posterity there. And so you find that my delta H for the entire formation of the entire equation is a negative 1397.82 kilojoules. Okay, pretty easy problem actually. Just consult your charts for those different heats of formation. Okay, one last thing to take a look at, and this is actually can be solved in a couple different ways. We could do this as a regular stoichiometry problem. We know how to do this from section 1. I see that we have 13.3 grams of aluminum. And we want to know how much heat is released if I have a delta H of negative 850. Well, I simply go with my 13.3 grams of aluminum. I go and say, okay, my aluminum has a formula mass of 27 grams per mole. And then I have 2 moles for every negative 850 kilojoules. Okay, and so I'll end up with an answer of negative 209.4 kilojoules. Okay, that's all I need to do. Now, if I want to take a look at the heat of formation of everything, that's going to be a little bit different because I would have, in this case, here's an element, that's 0. Here's an element, that's 0. If I take a look at my, let's see here, this is going to be my, let's see, this is going to be negative 826. Sorry, just looking at my chart. And this is going to be a negative 1676. Okay, so if I use my equation with this, the delta heat, or my heat of formation, is going to be 1 times the negative 1676 plus 2 times 0 plus 2 times 0 plus 1 times negative 826. Okay, so my heat of formation for the entire thing going is going to be negative 850 kilojoules. Okay, so that's just saying that value, if this is not provided for us, then we'd have to do our heat of formation to find it, and then I could take that value and plug it right there. Okay, so that, again, if I get stuck and they don't give me this line, then I'd have to actually run this and find my heats of formation in the first place. Okay, so that's pretty straightforward, guys. That's all we need to be able to do. Go slow through the process and make sure everything cancels, and you should be in really good shape.